Let us spend a little time today digressing to a topic in dynamical systems more properly taught in courses on physics, namely Hamiltonian systems, and I would like to bring out to you how special Hamiltonian systems are, and we studied Hamiltonian systems from the point of view not so much of mechanics as of our general study of dynamical systems and nonlinear dynamics. Before we talk about Hamiltonian systems, there is another class of dynamical systems which I would like to dispose of or at least mention very briefly in passing, and perhaps we might come back to such a system a little later in the course, and this is a class of dynamical systems called gradient systems. Recall our particular kind of dynamical system that we have focused on, namely those which satisfy autonomous coupled differential equations of the form f of x, where f is a prescribed vector field. It is a function which has really got n components in n dimensional phase space f1, f2, f3 up to f sub n, and these are functions of the coordinates of the variables x1, x2 up to x sub n. Therefore, to specify the dynamical system you have to specify a vector field at every point in some region of phase space. A gradient system is one where this vector field has a very special form. If this vector field is of the form the gradient of some scalar function of the variables x, I call this a gradient system. What's special about it, of course, is the fact that instead of specifying a vector field which means all its components, n functions f1 through to xn, f sub n, we need to specify just a single scalar function phi, and everything else, all the components of f are determined in terms of this single scalar function phi. So clearly it is a very special kind of dynamical system. Not all dynamical systems can be written in this form, but those that can clearly enjoy a little superior status among dynamical systems because a single scalar function suffices to tell you the flow at all points. Now of course the component of this, if I take the ith component, this implies that xi dot is delta phi over delta xi, and phi is a function of the variables x. That is what is meant by a gradient system. If you give me the function phi and I set phi of x equal to a constant, it would in general be a surface in this n dimensional phase space. So if schematically this is what the surface looks like at a particular point x, and this corresponds to the surface phi equal to a constant c, say, then what is the direction of the gradient of phi at this point? The gradient is defined as the normal derivative. The gradient of any scalar field is the normal derivative. It is the direction in which this function phi has the maximum rate of change, that direction along which it changes most rapidly. Therefore it is normal to the direction of the level surfaces of phi. So if phi equal to constant is a surface, the level surface phi equal to constant, then this is the direction of the gradient of phi at that point, which means the flow lines or the phase trajectories of a gradient system are always normal to the level surfaces phi equal to constant at each point. Now that is a useful fact to know. We do not come across too many gradient systems, they are somewhat rare in a certain sense, but when they do occur, then it is very useful to give a geometrical interpretation for the flow lines in this sense, namely the lines phi equal to, the flow lines are normal to the level surfaces of the scalar function phi, single scalar function phi. There is another very important class of dynamical systems called Hamiltonian systems, for which once again a single scalar function determines the vector field f on the right hand side. And now let me define a Hamiltonian system. These are systems which are always even dimensional in a very specific manner. They are described by a set of dynamical variables which occur in pairs, and therefore the total number of variables is always an even number. The first n variables are generally denoted by the q's, q1, q2 up to qn, and these are generally usually called generalized coordinates. And along with them go a set of variables p1, p2 up to pn, which are called generalized momenta. Therefore, the full set of dynamical variables x is a set of 2n variables q1 to qn, p1 to pn, 2n dynamical variables. The phase space of a Hamiltonian system is always even dimensional. It is conventional to call q's, the generalized coordinates, degrees of freedom. So this system has n degrees of freedom and it has 2n dynamical variables. Something very special connects each q to its corresponding p, called its conjugate momentum p, and that is a structure called the Poisson bracket, and I will define this as we go along very shortly. For the moment we will use this terminology which says that the q's and p's are conjugate to each other. q3 is conjugate to p3, q4 is conjugate to p4, and so on. The more strict term is canonically conjugate in a standard manner, and we will explain as we go along what we mean by this. The equations of motion are of particular interest. They are called Hamilton's equations of motion, and the most common occurrence of Hamiltonian systems is a set of particles moving, for example, under the influence of forces which they exert on each other, conservative forces which they exert on each other, or a set of particles moving under the influence of some conservative external force, or both. Mechanical systems very often turn out to be Hamiltonian systems in the absence of friction, in the absence of dissipation. So Hamiltonian systems will, in the sense we understand it, will be conservative dynamical systems. There will be special cases of conservative dynamical systems, and the equations of motion which correspond to our dynamical equations go by the name of Hamilton's equations, and they read as follows: qi dot is delta over delta pi of a certain scalar function h of all the q's and p's in general, and let me abbreviate that by just writing it as q comma p. That stands for all 2n variables in general, and this is true for each I from 1 to n. qi dot, and the rate of change of pi is again given by the partial derivative of the Hamiltonian, but with respect to the conjugate generalized coordinate qi with a minus sign, and this set of equations is valid for each I. It is not a gradient system, because the gradient system would imply that each time derivative of each dynamical variable is the partial derivative of some scalar function with respect to the same variable, but that is not happening here. The time derivatives of the q's are partial derivatives with respect to the conjugate p's and vice versa, but with a minus sign, and this minus sign is crucial, it is very very important. This is the general structure of equations when you look at particles moving in a potential, for instance. Yeah, there is a question.
Hello. What exactly? Are these properties, or what exactly is defined?
The question is, where do these things come from? This is the definition of a Hamiltonian system, but as soon as I finish defining this, I will go back to ordinary mechanics and show you that ordinary mechanical problems in the absence of frictional forces, these are the defining equations, these are Hamilton's equations, they define a Hamiltonian system. The original motivation was of course the observation that Newton's equations of motion in the case of conservative forces are essentially Hamiltonian equations, and this is a generalization of the idea which one already has from Newton's equations of motion. So let me do this in a formal way, and then we go back in a minute and see that ordinary mechanics is indeed a special case of Hamilton's equations of motion with a specific prescription for the Hamiltonian function. But right now I am doing this in a very abstract way, I am simply saying that if a dynamical system is even dimensional and has this kind of structure with certain additional properties which I am going to write down regarding the way the q's and p's are related to each other, then it is called a Hamiltonian system. Okay. So let us step back and ask, is this a gradient system? No, not as it stands, but you still have this wonderful property that the entire vector field on the right hand side is actually defined in terms of determined by a single scalar function, the Hamiltonian function. Okay. That is going to cause a great deal of create a lot of simplification, it is going to lead to a lot of simplification and very interesting properties. Now let us go back and ask, what happens if I take a single particle which is non-relativistic, ordinary Newtonian mechanics, moving in some conservative potential or field of force? What would you say are the equations of motion? A single particle moving in some potential. I could write down Newton's equations of motion, and the way to write it down in our language is to say that the mass times the velocity, which is dr over dt, is the momentum p, and the rate of change of momentum dp over dt is equal to the force on the particle. If this force is time independent, no explicit time dependence, and depends only on the instantaneous coordinate of the particle, then it is some f of r. And if this force is conservative, which means it is the gradient of some scalar potential which has the connotation of a potential energy of the particle, then this is equal to minus the gradient of a potential v, which is a function of the coordinates of the particle. This is what you would write down as the normal equations of motion. I have just written Newton's equations down, but as a set of coupled equations. Dr over dt is p over m, I could bring this to the other side, and dp over dt is some function of r. It certainly is a dynamical system in the sense we understand dynamical systems. What is the dimensionality of the phase space here? It is 6 dimensional because 3 coordinates and 3 momentum variables, so 6 coordinates, and it is exactly the structure that we had. X dot is some f of x, some vector field on the right hand side. So we have written it as 2 coupled vector equations, 3 dimensional vector equations in this fashion. The question is it of that form? Is it of this form at all? Can we write it in the form of Hamilton's equations. By hindsight we know we can, because we know that in ordinary mechanics with conservative forces the Hamiltonian of the particle has the connotation of the total energy of the particle, which is the sum of its kinetic energy and its potential energy. So we write H as a function of R and P, and these would be Q1, Q2 and Q3 in this case, and this the components of P would be P1, P2 and P3. If these are Cartesian components, then this is equal to P squared over twice the mass of the particle plus the potential V of R. And if I call these components Q1, Q2 and Q3, and similarly this has components P1, P2 and P3, it is immediately clear that these equations here really imply that Qi dot is indeed equal to delta H over delta Pi, because if I want to find out what dQ2 over dt is, we know from this set of equations here that dQ2 over dt is P2 over m, and that is precisely delta H over delta P2, and it also tells us that Pi dot is minus delta H over delta Qi. Since the potential energy depends only on the coordinates, when you differentiate with respect to the coordinates in Hamilton's equations, you end up with the corresponding component of the force. So this is an example of a Hamiltonian system, and the way I have defined it there in general, it generalizes the same idea to n degrees of freedom. And the simplest way of thinking of a Hamiltonian system is to look at the special case of a set of particles moving in a conservative field of force. Now that is an example, the standard example of a Hamiltonian system. There are many other Hamiltonian systems as well, but that is the simplest example. So Newton's laws of motion for conservative systems are definitely Hamiltonian. The prescription for writing the Hamiltonian down in conventional mechanics is fairly straightforward. You start with the Lagrangian of the particle and then you make a certain transformation and go over to the Hamiltonian, and generally in elementary problems it turns out to be the sum of T plus V. It is the sum of T and V, but T is the kinetic energy and V is the potential energy. That is the way we have written it down here, but it is much more general than that. This scaffolding is not necessary. A Hamiltonian system is defined by the set of equations, Hamilton's equations that I wrote down, the general equations, together with a certain connection, a certain structure called the Poisson bracket relationship between the Q's and P's, and let me define the Poisson bracket. Given the dynamical variables Q1 through Qn and P1 through Pn, if I look at any function of these dynamical variables, and let us call them A of Q and P, and any other function of all the dynamical variables B of Q and P, then the Poisson bracket of A with B is denoted by curly brackets A comma B, and by definition it is equal to a summation over all the degrees of freedom 1 to n delta A over delta Qi delta B over delta Pi minus delta A over delta Pi delta B delta Qi. This is the definition of the Poisson bracket of A with B. we need to understand a little more about the structure involved here, but it is these partial derivatives in this particular combination. If the q's, by assumption the q's are independent of each other and the p's are independent of each other, then it follows, if these are independent dynamical variables, it follows that delta qi over delta qj is 0 unless I equal to j, in which case it is equal to 1. Therefore, this is equal to the Kronecker delta. Similarly, delta pi over delta pj is delta ij, because the p's are independent of each other unless I equal to j, in which case it is identically equal to 1, and the q's and p's are independent dynamical variables. So delta qi over delta pj is always equal to 0. So you have two sets of dynamical variables, half of them are regarded as generalized coordinates and the other half as generalized momenta. They are independent dynamical variables, you need all of them to describe the dynamical system. So this is not surprising, and the fact that this relationship or that holds good simply says that different q's are independent variables, you need that many independent variables to describe the system. Once you have that, you could ask what is the Poisson bracket of a particular q with a particular p, and let us figure that out. So what is the Poisson bracket of qk with pl, for instance? What is this equal to? All you have to do is to plug it in here and do a summation over I and compute what the answer is using the statements we had earlier about the p's and q's. So what do you get? Well, this is going to become a delta ki and this is going to become a delta li. So it is 0 unless k is equal to I, and this term becomes 0 unless L is equal to I. So the answer is delta KL, because this term would anyway be 0 if you differentiate a q with respect to a p or a p with respect to a q, the answer is 0, and therefore it is equal to the Kronecker delta. What is the Poisson bracket of qk with ql? Both these quantities are now q's in the numerator and at least one of these will vanish, and therefore this is 0, and the same is true for pk with pl. This set of relationships between the generalized coordinates and the generalized momenta of a dynamical system, of a Hamiltonian system, are called canonical Poisson brackets. So these are the canonical or standard Poisson bracket relations. You might ask, why am I defining a Poisson bracket? Why is this? What is the use of this? And we will see very shortly what the practical use of this is. But meanwhile, this relationship here, this way of defining Poisson brackets, has got mathematical structure to it, very deep mathematical structure. Notice it is a bilinear operation in some sense. You give me two functions a and b of the dynamical variables of a Hamiltonian system, and I do something which involves both of them. It is a bilinear structure. In general, the right hand side is some other function of all the dynamical variables, and it has also got certain interesting properties of the following kind. A with b plus c, if you took two functions, the sum of these two functions as the second member of the Poisson bracket, it is quite clear this is equal to a with b plus a with c. is immediately obvious that this is so. If I multiply B by some constant which is independent of all the dynamical variables, then of course the constant comes out, and A with KB is equal to K times A with B, where K is some constant. And this quantity is also antisymmetric. So you have a natural antisymmetric bilinear structure here. Yes?
This canonical relations, they are coming up just because the coordinates are independent.
Absolutely,
So
absolutely. There is nothing great about it at this stage, but the fact is that these things have enormous implications. Once you identify a Hamiltonian system, then you guaranteed certain relationships automatically. So what we have done is the other way about. I started with mechanical examples and I told you Cartesian coordinates are independent of each other, and I wrote down certain relationships between them, but the fact is that structure generalizes to much more general context than just the usual ones you are used to. So it is simply that it is a very useful and a very general framework for understanding a huge class of dynamical systems, of conservative dynamical systems. Right now we are talking about some mathematical properties of Poisson brackets, and we are writing down relationships which are fairly trivial. They follow fairly straightforwardly from the independence of the coordinates and the momenta between each other, plus the canonical Poisson bracket relationships, but these have deeper implications, as we will see. What is the Poisson bracket of A with a product of two functions? So if I took A with BC and asked what this is equal to, you would have to use BC here and BC here and use the chain rule of differentiation repeatedly, and then it is a simple exercise to show that it is A with B times C plus B times A with C. This is a chain rule for differentiating functions, that is all that has been used, and then it leads to an identity of this kind. What would this be? What would AB with CD be equal to? What would you get on the right hand side? You would get 4 terms. So first treat AB as a unit and use this formula for decomposing it into Poisson brackets of AB with C and AB with D, and then use the formula again for decomposing this into 2 more terms. So you get a set of 4 relationships. So this is 4 terms on the right hand side. There is one more property of Poisson brackets which is crucial importance, and that is the following. If you took 3 functions A, B, C of the dynamical variables and computed A with the Poisson bracket of B with C, and then took the Poisson bracket of A with this plus the Poisson bracket of B with the Poisson bracket of C with A plus the Poisson bracket of C with the Poisson bracket of A with B, what would you guess is the answer? It is 0. It turns out to be identically 0 on using this property. So there is this antisymmetry when you take 3 of these guys, and the antisymmetry of the Poisson bracket leads to this property. It is easy to establish. Do these properties, you have got a set of objects A, B, C, etc., which are functions of the phase space variables in a Hamiltonian system, and among those functions I have defined a certain bilinear structure called the Poisson bracket. I take two of them at a time and I create something, a new function. That function has this antisymmetry property, and it also has this property which is called the Jacobi identity, and it has the usual properties such as A with the Poisson bracket of A with a scalar times B, constant times B is the constant times that of A with B, the Poisson bracket of A with B. It has the antisymmetry property and it has the property A with B plus C is A with B plus A with C. Does this remind you of something? Does this structure remind you of something? These 4 properties, do they remind you of anything else, any other example where you have exactly the same sort of properties? Yes? If you took ordinary vectors in 3-dimensional space, in Euclidean space, and you took the cross product of 2 vectors, what happens then? Do they have identical properties? If I took vectors A, B, C, etc., and I computed the cross product of 2 vectors, is this not equal to minus B cross A? And is it not true that A cross some scalar times B is K times A cross B? And certainly this is true too. And is this true? If I replace the Poisson bracket operation by the vector product or the cross product of 2 vectors, is it not true that A cross B cross C plus cyclic permutations turns out to be 0 identically on the right hand side? So exactly the same set of properties mathematically, a bilinear operation which is antisymmetric satisfies these properties and satisfies the Jacobi identity. Anything else? Can you think of any other structure which does exactly the same, any other class of objects which have similar properties? Suppose A, B, C, etc. were square matrices, n by n matrices of some given order, and instead of the Poisson bracket, instead of A comma B as the Poisson bracket, I replaced it by the commutator of the 2 matrices. This stands for AB minus BA. Then the commutator of 2 matrices is antisymmetric. The commutator of A with B is minus the commutator of B with A, and this property is valid for commutators, and so is this. Any set of elements for which such a bilinear product or bilinear operation exists satisfying the antisymmetry property, these properties as well as the Jacobi identity, is called a Lie algebra. So it says functions of the dynamical variables of a dynamic Hamiltonian system form a Lie algebra under the Poisson bracket operation. A very useful concept. We are not going to deal so much with the algebraic properties here in this course, but it is a useful thing to know that there is something deeper, a deeper mathematical structure to Hamiltonian systems under the Poisson bracket operation. So that is responsible. A lot of the properties actually are mathematical properties which have physical implications, which follow from this Lie algebraic structure of functions of the dynamical variables under the Poisson bracket operation. There is one immediate use of the Poisson bracket, and that is the following. In conservative mechanical systems such as those determined as where the Hamiltonian is simply determined as the kinetic energy plus the potential energy, we know that the energy is a constant of the motion. I now show you that the Hamiltonian itself for autonomous systems is a constant of the motion identically, and that is easy to see, because if I start with h as a function of all the q's and p's and I compute d over dt of this quantity, this is equal to, by definition, since it is a function of the q's and p's, this is equal to a summation over the degrees of freedom delta h over delta qi multiplied by qi dot plus delta h over delta pi multiplied by pi dot. Since it is a function of the independent variables q1 to qn and p1 to pn, its time derivative, total derivative, is just this set of partial derivatives multiplied by these total derivatives. But now we use Hamilton's equations of motion, therefore on a solution set, on a solution of the equations of motion, this becomes equal to a summation delta h over delta qi, and what was the equation of motion for qi dot? Delta h over delta pi plus delta h over delta pi, and what was the equation of motion for pi dot? Minus, the all important minus and of course this is identically equal to 0, which implies that the Hamiltonian of a Hamiltonian system, an autonomous Hamiltonian system, is a constant of the motion. You will appreciate the importance of that relative minus sign in producing this result. What is the equation of motion of any function of the dynamical variables? That too can be written in a very simple way, and that will bring out the use of the Poisson bracket. So let us suppose A is a function of the q's and p's, and I ask what is the rate of change of this function of the q's and p's, and I use exactly the same technique as I used earlier, and what would this become? This would become a summation from I equal to 1 to n delta A over delta qi times qi dot, but qi dot is delta h over delta pi. I put that in, pi plus delta A over delta pi times pi dot, which is minus delta h over delta qi. So they get minus but what is this equal to? The Poisson bracket of A with h. Now that is a remarkable fact. It says the rate of change of any function of the dynamical variables is just the Poisson bracket of that function with the Hamiltonian of the system. That tells you the fundamental role played by the Hamiltonian. Of all the functions of the dynamical variables of such a system, the Hamiltonian is predominant, plays a fundamental role because it controls the rate of change with time of every other function. When is this a constant of the motion? Yes, when A Poisson commutes with h, when the Poisson bracket of a function with the Hamiltonian is 0, if it vanishes identically, then the function is a constant of the motion. and the converse is true as well, as long as we are dealing with autonomous Hamiltonian systems. Of course you could generalize Hamiltonian systems to non-autonomous systems, and then this is no longer true, because if you have a non-autonomous, and let me take a digression for a second and talk about non-autonomous systems, although would imply that there is also explicit time dependence on this side. What would happen then? What would happen then? What would the right hand side be modified to? Plus the partial derivative of h with respect to time. The explicit time dependence gets differentiated, and of course this portion vanishes identically, and you are left therefore with is equal to delta h over delta t, and if h is non-autonomous, that right hand side is not identically 0, and therefore the Hamiltonian is not a constant of the motion. Not surprising, because it is actually explicitly a function of time and it is not a constant of the motion in this sense. What happens if I consider a function a of the dynamical variables which also has an explicit time dependence, independent of whether the system is autonomous or not? So independent of this, I consider a function which has got explicit time dependence. What should I add on the right hand side? I should add plus delta a over delta t, and therefore it is this plus delta a over delta t. We need to modify this statement then. We already saw that you could have constants of the motion which had explicit time dependence, because the time dependence from the explicit t dependence could be cancelled by that of dynamical variables, the other dynamical variables in this combination. So we now come to the conclusion that a of q p t is a constant of the motion provided a comma h is equal to minus delta a over delta t. So if the right hand side vanishes, then the total derivative of this function with respect to time vanishes and you have a constant of the motion. So this is the test. This then is the test of when something is a constant of the motion. We are going to look at some other remarkable properties of Hamiltonian flows or Hamiltonian dynamical systems, and the most important one of them for our purposes is the fact that it is a conservative system in the sense of what we meant by a conservative system, namely that volume elements do not change in phase space under the flow, and let us verify that. Recall that when the dynamical system was given by x is f of x, then this was conservative if del dot f vanished identically, or this was identically equal to 0, then we called it a conservative dynamical system. Well, we now have a Hamiltonian system for which our x is really q1 to qn, p1 to pn. It is a 2n dimensional dynamical system. What is the gradient operator in this terminology in terms of the q's and p's? The gradient operator is one which has components which are the partial derivatives with respect to all the dynamical variables. So it simply stands for delta over delta q1, delta over delta q2, delta over delta qn, delta over delta p1, delta pn. And recall our equations of motion. The equations of motion were qi dot was delta h over delta pi but Pi dot was minus delta H over delta Qi. Therefore, if I simply compute this divergence here, it gives us a very simple result. Therefore, del dot F in this case was equal to what? It is equal to delta over delta Q1 F1, but F1 is delta H over delta P1 and so on. So this is equal to a summation I equal to 1 to n delta over delta Q1 Qi delta H over delta Pi. That takes care of the first n contributions to del dot F, and the remaining n are delta over delta P1 times minus delta H over delta Q1 and so on. So you also have minus delta over delta Pi delta H over delta Qi. On using Hamilton's equations of motion. But what is this equal to? It is identically 0, since you can take partial derivatives here in either order. If this function is integrable, then you can take partial derivatives in either order. Therefore this vanishes identically, which says that Hamiltonian systems have flows such that the volume elements in these systems are preserved in time. The flow is like that of an incompressible fluid, or the volume is preserved in Hamiltonian flows in phase space, and this goes by the name of Liouville's theorem. Or preserved is a better word. Again, a fact of great significance. It is not just volume elements that are preserved. Many other things are retained as constants also under Hamiltonian flows. So it is very restrictive. These conditions, the conditions which are imposed by this set of equations plus the Poisson bracket structure between Q's and P's, are actually very restrictive, and they have very deep implications. There is a very rich mathematical structure to Hamiltonian flows, some of which we will uncover subsequently. Okay. I start by saying it's not a result of this structure. No, not at all. No, it's not a result of this structure. I'm not saying it's an additional constraint. I'm saying that you define a Hamiltonian system as a set of 2n dynamical variables in which the variables are paired off pairwise, each q with its conjugate p, such that the Poisson bracket of each q with the p with its conjugate p is 1, and the Poisson bracket of each q with all the other variables is 0, and similarly for the p's. Together with that you specify a certain function of all the dynamical variables called the Hamiltonian, and the equations of motion have this structure. That is my definition of a Hamiltonian system, and from that everything else follows, including the fact that the Hamiltonian is a constant of the motion for autonomous systems, the fact that any dynamical variable or function of any dynamical variable, its rate of change with time is given by the Poisson bracket of this variable with the Hamiltonian for explicitly time independent variable functions, and Liouville's theorem which says volume elements are preserved. Various other things are preserved as well, we will not go into that. For instance, if this is a volume element, schematically you have some volume element of this kind in phase space, in 2n dimensional phase space, you could project this volume element onto each QP plane. So I take each Q and its conjugate P, and that forms a 2-dimensional plane, and I project the shadow of this onto this QP plane, and I take the sum of all these shadows of these areas. So I project onto Q1 P1, Q2 P2, Q3 P3 up to Qn Pn, and I take the sum of all the areas, and it turns out as this volume element flows, not only does it maintain its volume, the size, the magnitude of this volume is not changed, it might get distorted but it maintains its volume, but in addition the sum of all those shadows, those areas, is also preserved, it is also constant. That is a very remarkable fact. So it is not very intuitively very clear why this should be so, but it follows, all these properties follow from the structure of these equations. It is not a gradient system, as you can see, but I could write it as something which looks like a gradient system, and there is a mathematical structure here called the symplectic structure, which I am not getting into right now. Perhaps a little later I will mention a few properties of this extra structure as we go along. And as a prelude to that, let me do the following. Let me define a matrix J, a 2n by 2n matrix with the following kinds of elements. So let me define this J as a 2n by 2n matrix with n by n blocks here, and I have the null matrix here. This stands for n by n null matrix. I have the unit matrix here, and this stands for the n by n unit matrix. Minus the unit matrix here, and the null matrix once again here. So it is partitioned into 4 blocks, n by n blocks, and it looks like this, and I call this matrix J. It is a numerical matrix, it has just zeros and ones or minus ones as the elements. This is a diagonal block here with ones here, and this is a diagonal block with minus ones here. These are null matrices. Then it is not hard to see that the equations of motion in this case, in the Hamiltonian case, which are xi qi dot is delta h over delta pi, and pi dot is minus delta h over delta qi. This set of equations can be written almost in gradient form, in the form x dot is equal to j times the gradient of h, where by the gradient I mean a 2n component differential operator with components delta over delta q1 up to delta over delta qn, and then delta over delta p1 up to pn. And once I put this matrix J here, then it is nothing but the gradient. This twists in such a fashion that the q's, the rate of change of the q's depends on the derivative with respect to the p's, and vice versa, with a minus sign, and that is the reason for this minus sign here. So if I wrote this x as a column vector, 2n dimensional column vector, q1 up to pn, and similarly for the gradient of h, and then multiplied it by j, you would end up with just this. So this j does the required trick of converting the part, the rate of change of the q's will depend on derivatives with respect to the p's, and the p's with respect to the q's, but with a minus sign. And this structure has a name, it is called the symplectic. This matrix J has remarkable properties. What is the square of J? Well, it is immediately clear from this that the transpose of J is minus J, because these guys would go there and those fellows would come here. What do you think is the square of J? I leave you to figure this out. Incidentally, when n is 1, then a large number of the properties become quite transparent, because then you have a 2 by 2 matrix, which is essentially for n equal to 1 implies J equal to 0, 1, minus 1 and 0, and of course you could square this very trivially. I leave you to figure out what J squared is, then we will look at some interesting properties of Hamiltonian systems in this language. The advantage is that it looks very much like a gradient system, so you can write these things down much more compactly in this form. Okay. And one final comment, we started with mechanical systems and said you have the coordinates and you have the momenta, and they are quite physically distinct from each other. But now in an abstract setting, when we talk about Hamiltonian systems as systems defined by just a set of 2n variables of this kind paired off 2 at a time, then the distinction between what you call momenta and what you call coordinates can be actually lost completely. You could make changes of variables of these dynamical variables in such a way that what looks like momenta initially could turn out to be coordinates, belong to the set of coordinates, and vice versa, provided of course you put in factors for the right dimensionalities of these variables. I bring this up because the conventional notion of momentum as a linear momentum is very restrictive, because after all you could also have an angular momentum. You could have generalized coordinates which are angles, and the conjugate momenta would be angular momenta. So the momentum variables could have dimensions of angular momentum, not necessarily linear momentum, and the generalized coordinates could be angles which are dimensionless, they do not have to be lengths. So the advantage of looking at it this way is that you can go beyond the normal mechanical examples and look at the actual structure of the dynamical system per se, which is very intricate, very interesting, and has very, very crucial properties. So we have seen today, to summarize, that Hamiltonian systems form a special class of conservative dynamical systems, autonomous Hamiltonian systems. Liouville's theorem asserts that the volume elements are preserved in phase space, which conforms to our definition of what we said was a conservative system. The rate of change of any dynamical function of the dynamical variables is given by the Poisson bracket of these variables with the Hamiltonian, and the Hamiltonian itself is a constant of the motion. And the Poisson bracket idea enables us to identify other constants of the motion. So we will take it from this point tomorrow.